Good afternoon. I found something else I'd like to just draw to your attention. It's an article about fundamental science. About the effect of artificial intelligence on it. So the title of the article is "The Dawn of Post-Theory Science." It's an article from the Guardian Weekly. So does the advent of AI and machine learning mean that the classic scientific methodology, hypothesize, predict, and test, has had its day? Well, Isaac Newton apocryphally discovered his second law after the one about gravity, after an apple fell on his head. Much experimentation and data analysis later, he realized there was a fundamental relationship between force, mass, and acceleration. He formulated a theory to describe that relationship, one that could be expressed as an equation, F equals ma, and used it to predict the behavior of objects other than apples. Contrast how science is increasingly done today. Facebook's machine learning tools predict your preferences better than any psychologist. AlphaFold, a program built by DeepMind, has produced the most accurate predictions yet of protein structures based on the amino acids they contain. Both are silent on why they work, why you prefer this or that information, why this sequence generates that structure. You can't lift the curtain and peer into the mechanism. They offer no explanation, no theory, they just work. We witness the social effects of Facebook's predictions daily. AlphaFold has yet to make its impact felt, but many are convinced it will change medicine. So the article deals with a number of objections. The final objection to post-theory science is that there is likely to be useful old-style theory, that is, generalizations extracted from discrete examples. It remains to be discovered, and only humans can do that because it requires intuition. One reason we consider Newton brilliant is that in order to come up with his second law, he had to ignore some data. He had to imagine, for example, that things were falling in a vacuum, free of the interfering effects of the air resistance. In Nature, the mathematician Christian Stumpf of Ruhr University, Bochum, in Germany, called this intuitive step the core of the creative process. But the reason he was writing about it was to say that for the first time an AI had pulled it off. DeepMind had built a machine learning program that had prompted mathematicians towards new insights, new generalization in the mathematics of knots. So knots, the application of mathematics to knots is part of operator algebra theory. So you should look it up. Look up the Jones polynomial if you're not familiar with it already. Jones was an operator algebraic. In 2020, well, this was a year ago. In 2022, therefore, there's almost no stage of the scientific process where AI hasn't left its footprint. And the more we draw it into our quest for knowledge, the more it changes that quest. we can reassure ourselves about one thing. We're still asking the question. As Pablo Picasso put it in the 1960s, computers are useless. They can only give you answers. Oh, let me just go through the list quickly. Husam engine. Husam? Oh. Abigail Arsenal, thank you. Alexander Bullen. Jack Cerrone. Okay, thank you. Yuja Cheng. Oh, thank you. Carissa Cho Lee. Thank you. Arkaprabha Chowdhury. Oh, thank you. Siddharth Dagar. Daniel Bima. Justin Booth. Sabek Germani. Charles Griffin. May Grover. Henry Hu. Jalal Casa. Oh, thank you. Oh, you're Jalal. But the real Jalal, please stand up. Okay. No, but you're Vincent. Okay, that why? Is that why? No. Okay, but I I don't know if I can. What's your last name? H-A-N. Oh, Huang. Oh, okay. It's here. It says Xiao Hua Huang. Okay. Okay. Sure, but all right. Well, all right. Good. So I should have mentioned your name before Jalal Kasab's name. Yeah. Alphabetically. All right. Alexander Cole. Zhao Shang Lin. Luke Lacut. Thank you. Abu Bakr Mohidin. Ruben Navasarjan. Jonathan Ing. Oh, thank you. I don't have any homework for you yet. I had a lot of people I don't have homework from, but you're sorry? You forgot four homework. Yeah. Good, okay. All right. Rishi Praka. Syed Mohammed Raza. HY Shi. Lawrence Sai. Elon Wang. Hongbo Wang. Can you go? Okay, well, there's the various ideas in this course are quite closely related. An underlying theme is bot periodicity, but also another underlying theme is classification, and one reason these two themes are related is that to classify things, you look at K0, well, for AF algebras, you look at K0, and there's K1 too. Well, K1 of an AF algebra is 0. But if it weren't for bot periodicity, you'd have to look at the complex feature algebra, the usual setting. over the complex numbers. You'd have to look at K2, K3, K4, and so on. But this is all this is all taken care of by K0 and K1. This is why it's very different. And you do have to use K0 and K1. For AF algebras, you use K0. Well, let's take a look at why we don't need K1 for an AF algebra. Did anyone want to comment on that? Why don't we talk about K1? Well, actually, as I mentioned earlier, there is a way in which K1 gets used for AF algebra. If you have an ideal and the quotient which are AF, and it follows that the extension algebra, large algebra, is also AF. And the proof of that is, from a conceptual point of view, it's more or less immediate corollary of Bott periodicity. Okay, and why is that? Well, does anyone remember any of my comments on that, or have I looked it up? You come across it? Briefly?
You did the diagram, right? You have the K0 and K1.
Yeah, you're right. These are functors of K0 of the ideal, K0 of A, K0 of the quotient. And then you have K1. I like to write everything from left to right. So some people flip it. They think a circular diagram is more elegant. But well, I said this before. What I think people don't realize is that, and by the way, there are index maps like this, going from the K1 of the quotient. The even index map goes to K1 of the quotient, K0 of the algebra. And the odd one goes from, they exist in the over complex scalar, it goes from K0 the quotient to K1, which is why it's called odd. Sometimes. Okay. It's, I don't know why, but I get a kick out of, yes,
Sorry?
sorry?
The K1 group is the K0 group of the suspension.
Yes, that's right, yeah. And you have to remember, we haven't discussed the non-unital algebras, right? But the suspension, unless it's zero, will always be, unless the original algebra is zero, the suspension will always be non-unital because it's continuous functions vanishing at infinity. If you had a unit, its norm would be continuous, right? So it couldn't vanish at infinity. The norm at a point, at every point, the value, it's a function of values in the algebra. And if the values could include the unit, then if they were a unit all the way, then the value, the norm would be equal to 1 everywhere on the line. So, okay, so no unit. But then how do you get K0 for non-unital algebra? Well, the short answer is you just adjoin a unit. That's why there's an exercise if adjoining a unit. This gives you, of course, to do this, all you have to know is adjoining a unit gives you an algebra with unit. But yeah,
isn't there an equivalent where the time K1 is equivalent?
well, sure. Well, we haven't actually got. Oh, no, we did get to a definition. You look at K0 of the suspension, right? Okay, well, and it's true that for Banach algebra with unit, you can get it by talking about by talking about invertible elements. And for a C-squared algebra, it's enough to look at unitary elements. Okay, well, that's a good exercise that it comes out to the same thing. That's quite important. So we should talk about that. That's a very good point. So if you're going to prove something like this, construct the index map. It's you have to decide what the best way to define K1 is, what the most convenient definition of K1 is. And okay, but the fact remains that when you look at an ideal of an algebra, well, the ideal is very unlikely to have the unit. Okay, because if it couldn't have the unit, if it was a proper ideal, it couldn't contain the unit of the whole algebra. It would have to be equal to the whole algebra in that case. But even if it has just its own unit, then the ideal would there would be a complementary ideal. The whole algebra would be the direct sum of two ideals with intersection 0, and the all products between elements from the two ideals would be 0. It might be called orthogonal ideal. The whole algebra would be the direct sum of two orthogonal ideals, which is quite special. For instance, if you look at the compact operators contained in algebra bounded operators on the Hilbert space, then I guess that ideal doesn't have a unit because the unit isn't compact, and so now just because it is a direct summand doesn't mean that it has to have a unit, right? If you take any algebra whatsoever, take the direct sum of two copies of it, then you'll have two orthogonal ideals in the direct sum algebra. But okay, but one way or another, you define K1. It's a functor. If you define it as K0 of a suspension, then it's maybe you can say it's a functor as soon as you know K0 is a functor, because the suspension is an actual operation, factorial. So, but okay, let's look and see what the best definition of K1 is to prove that K1 of an AF algebra is 0. Okay. How are we going to? Why is it true that K1 of an AF algebra? So the point is that when I is an AF algebra, the ideal is AF, then the K1 group is going to be 0. Okay. But then this 6-term exact sequence says that the map, the canonical map, the functorial map from the algebra, the unknown algebra, onto the quotient, the level of K0 is surjective. Okay. Is everyone familiar enough with diagram tracing to see that? It's an exact sequence. It's an exact sequence. Abigail, have you run into what an exact sequence is? Yeah, exactly. If you as soon as you say kernel, then that's I can see you know the answer. Currency, do you know the answer? So what's the other word besides kernel? If you have, yeah, okay, but and what's the important relationship between them? Yeah, okay, that's what exactness means. If you have a map going, a diagram with a map going into it, and then another map coming out of it, and there's just one map in each case, one map going in, one map coming out. So the diagram is exact at that point if the image of the map going in is as a sub object of the object that you're talking about is equal to the kernel of the map going out. Okay, so these, now image always makes sense for a map between sets. Kernel is restricted to vector spaces, right, or groups. But we're talking about algebras, and in particular, they're vector spaces. So the kernel should be equal to the image. But then if the image is 0, then that means the kernel is everything, right? The kernel of the map of this map. Well, I wanted to repeat my little joke that you might think that these two that this diagram is quite messy because the two index maps cross over, right? That's it. Okay, you might want to go in a nice circle, so you might want to flip this one, so it goes like that. That's what is quite common for people to do. But to me, that's a really funny joke because any, well, this particular plane diagram, in any case, it can be distorted so that it's in the plane. It doesn't, none of the lines cross over. Okay? Everyone agree? Yeah. You just take this, you consider it as a string, and just take it and you move it up. So, okay. If it bothers you, yeah. Okay. And the idea of going left to right on the functor side, that's just, I mean, that's just, I wouldn't be able to remember anything without keeping track of that. Without that help keep track of them. Okay, but so the now we're talking about now if the big algebra is AF, that means if you have a projection here, it will be the image of a projection here. It'll lift to a projection there. That's an easy exercise. And by the way, to prove this theorem, it's enough to consider the case that this is just a complex number. The quotient is just one complex number. And then, well, so maybe two copies of the complex number. And but so but so at a certain point, before it was proved that using periodicity, that projections do lift. Every projection in the quotient comes from a projection in the algebra, which is true if it's a necessary thing you have to prove. If A is going to be AF. But it's also sufficient because I had developed enough technical tools to prove that the A had to be AF if you knew the projections always came from projection. That says at the level of projections, the map is surjective, right? But what is K0? K0 is projections. K0 is idempotent. So the map, if we have if the map coming out of K0 of the quotient is 0, that means the map coming in is surjective. That means every K0 class for the quotient comes from a K0 class here. So K0 classes lift. Okay, K0 classes come from K0 classes. And we want to prove that the projections come from projections. Well, what's missing? If projections are essentially K0, if K0 classes are essentially projections, then if you know that the K0 classes downstairs come from K0 classes, why don't you know the projections come from projections? Well, there's a bit of a bit of a song and dance to establish that. For one thing, the K0 classes don't come from single projections; they come from pairs of projections, right? Because that's how if you have a semigroup, a semigroup consists of the classes of the so-called equivalence classes, Murray-Van Emmon equivalence classes of single projections. by the board. And then if you look at the enveloping group, the universal enveloping group of the semigroup, then you look at pairs of elements, right? If you want to construct integers from natural numbers, you look at ordered pairs of natural numbers. When do people normally do that in school? When do people first learn about integers as pairs of natural numbers?
Oh, you can as pairs of natural
Sorry?
as pairs of natural numbers?
Well, if you just look at single natural numbers, those are natural numbers. But if you want to look at pairs, if you want to look at integers, then you have to have two natural numbers so you can subtract.
Oh, okay.
Just like when you're defining index.
I didn't really learn that.
Okay. But so in particular, no, when you're defining a group from a semigroup, you always look at pairs of elements in the semigroup, and you look at equivalence classes of those pairs, and what this does is allow you to say that the equivalence class is something like the difference between these two individual things. It's what you might call the formal difference. You can't have, if you're just given a semigroup, you don't know how to subtract. Okay, and don't forget that when we map it, when we construct this enveloping group, the semigroup may not map injectively, may not actually be contained in the enveloping group. So it makes it slightly complicated. In fact, the map may not be exactly. In fact, the group might be zero. The enveloping group might be zero, and the semigroup is non-zero. I guess an example of that would be the semigroup 1 plus 1 equals 1. Okay, what's the enveloping group? You can? Yeah, the semigroup is a single element 1, or we'll call it 1. Maybe call it x, and the addition is x plus x equals x. So that's a semigroup, right? Okay, so what's the universal enveloping group? Sorry? Well, x isn't anything. I mean, you have to say what the operation is. If you want to define a group, it's not enough to say what the elements are. Well, yeah, but we're talking about addition, right? But okay, but then what is the addition? If you call the single element, I mean, obviously, well, it might be more than a single element, but let's assume it's right. That the universal enveloping group just has a single element x, and x maps into x, embedding the mapping from the semigroup into the universal enveloping group is taking a single element x into x. Okay, but then if in the semigroup the addition operation is given by x plus x equals x, well, the map into the group is additive, right? So so in the group you're going to have x plus x equals x, right? Well, actually that means that x is 0, right? But it's also true in the semigroup. It's also true in the semigroup. X is 0 in the semigroup because x plus x equals x. X plus anything is the anything. So that means that the semigroup is already a group in that case. So it wasn't a very good example where the mapping wasn't injected, okay? So, but suppose you take the semigroup with two elements, 0 and 1, 0 and 1. And then 0 plus anything is the anything. And then 1 plus 1 equals 1. How about that? Now the question is, what is the group? Well, I guess the 0 is going to go into the identity element of the group. But also, just like before, the x is going to have to go into the identity element of the group, because if in any group, if you have x plus x equals x, then x must be 0, right? Okay, so everything goes into 0, but the semigroup is not. It doesn't. It has two elements. So that shows that the universal developing group isn't always doesn't always contain the it's generated by the image of the semigroup, but it could be 0, and the original semigroup is non-zero, for instance. Okay, so but in general, the well, this isn't really addressing the question of what the construction is. Why you well generally you look at the formal difference, what's called the formal difference of two elements of the semigroup. That means two projections. Okay, so the formal difference is two projections, and so if the projection here is E, then upstairs you have F1 plus F2, and the class of F1, the K0 class of F1, minus the class of F2 would map to the class of map to the class of E. Okay, and but so the class of E lifts to something. Now suppose it lifted to a projection. Suppose F2, if F2 is 0, then F1, the class of F1 by itself maps into E. But then now I think it's a good exercise now to show that in the present setting where the quotient is an AF algebra, the F1 itself maps into a projection. So always the F1 maps into a projection, E prime, projection, homomorphism, star homomorphism. And if it's an AF algebra, then E prime is unitarily equivalent. This is equivalent to E, unitarily equivalent, okay? And so you can, since unitary is in a do lift, you have a unitary in a AF algebra, it always comes from a unitary in the algebra. Well, yeah, that's always true. It's not always true for projection. Because we're using the ideal as K1 equals 0. Okay, but so the idea is to somehow get rid of the F2. Well, one way to get rid of it is to take it over to the other side somehow. If you if you add the class of F2 to both sides, you get the class of F1 goes into the class of E plus the class of F2 dot, okay, which is the image of F2, another prediction. We could by choosing different representatives, we can make sure that the F2 dot is orthogonal to E. But then that means that the E plus something else can be lifted, and something else can be lifted too. So you can. Well, the final strategy of the proof is to show that if the E plus something else can be lifted, and the something else can be lifted, then the E can be lifted. If you have to fiddle a bit to do that. So this is a interesting theorem. I'm not going into the proof right now, because this could be an essay program, right, to look it up. It's, look it up and or work, try to work it out without looking it up. But I'm just outlining it now in order to show how important for instance, even just for the theory of AF algebras, this bot periodicity is how important it is. Okay, so now the horizontal maps are come from functoriality, and it turns out that the even index map exists without assuming complex scalars. If it's real scalars, then it's any real Banach algebra. Or, I mean, it's hard to define a real C-star algebra, but a real Banach algebra is quite easy to define. And this works for Banach algebra too. That's one reason people talk about idempotence a lot in C-star algebra theory rather than production. And that's because to prove bot periodicity, at least the proof in the book, doesn't prove it for a C-star algebra at all. It proves it for a Banach algebra, complex Banach algebra. Then you have to know that idempotents give you the same K0 group, and the invertible elements give you the same K1 group. Well, okay, but then the reason this having this 6-term exact sequence is considered to be equivalent to bot periodicity is that the special case of it is it is the case of bot periodicity that that there's a natural isomorphism between K0 of the suspension and K1. Okay, with a certain special extension, a certain special A and ideal quotient, then you get that then the exactness here and here gives you that K0 of the suspension is isomorphic to K1 of the algebra in a natural way. But conversely, if you assume this is true, that taking suspension just flips K0 and K1 means also true that K1 it's not so deep, but it's interesting that K1 of the suspension is isomorphic to K0. Okay, but we're taking the suspension just flips K0 and K1. All right. But suppose you look at this diagram without the odd index map, as it which only uses that the algebra is a real Banach algebra. Okay. Then you use that it's a complex Banach algebra. Well, the first row is K0, and the second row is K0s of the suspension. Well, roughly speaking, you just flip the diagram vertically, okay? And this arrow, take the even index map goes into some map from the upper right to the lower left, which is exact here and here, and you just call it the odd index map, and you can calculate what it is. There's a somehow tantalizing construction of a map here. In the case of a complex Banach algebra, forget about assuming bot periodicity. You can construct a map, okay? But you don't know you get exactly. You have to prove that. That's what requires the bot periodicity. But it's, in fact, it's so easy to construct a map. I can't resist doing it right now. It shouldn't take long. So but it definitely only makes sense for when you have complex numbers, complex scalars. And by the way, that Riship's suggestion to take unitaries is going to come in because if you have complex scalars, a complex Banach algebra, or a C-star algebra, you get a self-adjoint element. Would you have a self-adjoint element? Would you have a self-adjoint element in the C-star algebra? Okay. Well, then you take I times take I times the self-adjoint element. Okay. We're definitely using complex scalars. And now you exponentiate. Everyone know how to exponentiate? Does everyone who talks about exponential growth, do you think they know how to exponentiate? Well, sometimes you can do it without thinking. In fact, just about everything is exponential growth, I guess, or decay, exponential growth or decay. So, so one good example of that is radioactive chemicals, radioactive substances. They will, the amount of substance left will decay in time. Okay, and if it's extremely radioactive, then it's very, very dangerous. But it will tomorrow it'll be gone. Okay, people don't know that. They just think of it as being very dangerous. Or on the other hand, if some radioactive substances last for an extremely long time. Well, that means they're hardly barely radioactive, right? So it seems to me that most people are not, even though exponential growth and decay are the most common things, I don't think they are taught in school. So how many people know how to exponentiate in a Banach algebra? Okay, Arthur. You do it with a power series. Okay, and it's the same coefficients as for ordinary numbers and real or complex numbers, and always it converges, right? And if the algebra is complete, I mean, you get a Cauchy because of the algebra norm inequality. So the norm of the nth power is less than equal to the nth power of the norm, and so if the norm is, but then of course the norm may be bigger than 1, but you're dividing by something which is much larger. Sorry, okay. We're always convergent. Okay. Well, now if you look at the exponential of I times h, it belongs to the C-star algebra. Okay. Well, if h is self-adjoint, then what's going to be special about this element? That's a 10 may? Sorry? Okay, that's going to be true if h is a projection, and so you're saying that each of the IH will be the unit element. Is that what you're saying? I couldn't quite hear. Oh, well, that's true. Yes, that's true, and it'll be normal because h is normal, and its inverse it'll be invertible because it's an exponential, and the inverse will also have norm 1. Well, a normal element with that property is what is called what? Charlie, were you about to? Can you answer that question? No. Let me just redirect you. your willingness to answer. So you have a normal element of a C-square algebra, or a normal operator in a Hilbert space that has norm 1, and it's invertible, and its inverse has norm 1. Then what can you say about it? Vincent?
It's on the unit sphere. It's on the unit sphere.
Well, the spectrum is on the circle, okay?
Right.
But it, given, yes, Daniel. Right? Well, are you saying unitary?
Yeah.
Okay, yes, that's exactly right, okay? If it's a normal matrix, for instance, or a complex number, which the spectral theorem allows you to reduce to the case of the complex number. Complex number, its norm is at most 1, say, and its inverse is norm has norm at most 1. Well, then it sits on the circle, right? Yeah, so it's called unitary. All right, well, but then Rishi was talking about unitarities a while ago. That gives you something in K1, right? And that's what we're looking for. And it's, by the way, it's in A. But K1, we want K1 to be ideal, okay? But that means that it could essentially be in the ideal, okay? We want it to be in the, we want it to be, actually, we want it to be in the ideal with the unit adjoint, okay? The ideal with unit adjoint. Where we're assuming that the algebra has a unit. Well, you define the exponential. Your first term is in the power series is the unit, right? 1 to 1. Okay. So, but then this is equal to the kernel of the map from A to A over I, plus at least I itself is. So what I want to do, I want to show what happens if I map this to A over I. It's in A. What happens if I map it to A over I? Well, H goes into oh, okay. So I, I'm not talking about an arbitrary self-adjoint element. I'm talking about a projection. Okay. I want to map from K0 of the quotient to K1 of the ideal. So I start with some projection in A over I. And then now we don't know a projection lifts to a projection, but it certainly lifts to a self-adjoint element. Because you lift it to something, you lift it, take the projection, lift it to something, and then take the average of that with its adjoint. And that will map in, that'll be self-adjoint and will map into the projection. So any projection has a self-adjoint lifting. But now, if H that goes into I times E, right? So I guess I want 2 pi I times H. 2 pi I times H. Well, now, if I mean, that won't affect whether it's unitary or not. But then, if H, if 2 pi I H goes into 2 pi I times E, then the exponential will go to the exponential, right? And what's the exponential of 2 pi I times E? What's the exponential? Forget about the case. What if E is 0? What's the so E is a projection. E squared equals E star equals 0. Okay. And so I want to know what the exponential of 2 pi I times E is. Well, follow Professor Jack. Okay, well, that's too long an answer. You should always look at a special case archiprave. Itself? Yeah, yes. I don't know. I'm not quite sure what you were going to say, archiprave, but Jack is saying that that you have a projection in a in a C-square algebra with units, and and you need the unit to define the exponential, right? Then the exponential of 2 pi I times the projection, it doesn't matter what the projection is. If it's 0 or 1, or the identity in 2 by 2 matrices, well, in that case, you won't get 1 in the original algebra, you get 1 in the 2 by 2 matrices. Well, if it's exponential with respect to the algebra 2 by 2 matrices. That's slightly more complicated, but if it's just an algebra with units, then it's even true for item poles. It doesn't have to be self-adjoint. The exponential of 2 pi I times any item pole. So there's a good exercise, okay? Okay, well, that's true, but I don't know how well known it is that it's actually equal to 1 for an item pole. Maybe you have to think of it, okay? I know how to do it. Well, so at some point I distinctly recall I knew how to do it, okay? So if someone, if people's curiosity becomes overwhelming, then I can figure out again how to do it. But for self-adjoint projection, for self-adjoint item potent, it's a piece of cake. I mean, the spectral theorem comes in, and it's a normal element, and the spectrum is, to do the spectrum, you just work with complex numbers. You have any, the only complex numbers that are item potent are 0 and 1, right? You just have to check 2 cases. Well, okay. All right. How are we doing? I guess I'm promising a lot of things, but we'll have to see how that goes. And any questions? If there's an exercise that you want to do, yes. No question? Okay, but what exercise are you working on? You should always be working on an exercise, okay? So what exercise are you working on? Sorry? And what does it say? Oh, okay. All right. I mean, it's linear algebra. Okay, well, that's if we're working with the fundamental theorem of linear algebra, you have to be careful you don't assume that dimension is additive, right? The dimension of a direct sum is the direct sum of the dimension. You have to prove that. You define dimension maybe as what I would call fake dimension, to make sort things out, make it simple, you make it clearer what's happening. You just take the number of elements in the basis, the smallest possible number of elements in the basis, and that's a particular number, right? And then you have the direct sum of 2 vector spaces. You have the union of 2 bases would be a basis. And so the fake dimension will be at most the sum of these 2 fake dimensions. But you have to prove it's equal. And that's that might be what the exercise is. I'm not sure. Okay, but that's a good exercise, right? How do you prove that? Well, you can prove it from first principles, but one idea would be to prove it from the fact that K0 of the field is Z. Okay, so that's a good exercise. And maybe an easier one is to prove it using the Murray von Neumann semigroup. If you look at some, say, finitely generated vector spaces, isomorphism classes up to addition. Okay, so assume that those things are labeled by natural numbers starting with 0, and use that to prove that that fake dimension is that gives you a map into the semigroup, and so it's additive. Okay, but that's very good exercise, I would say. And then there's a bonus. It's like riding a bicycle if you're 8 years old. Look, ma, no hands. Okay, you forget. You just look at the generated group. You forget about the semigroup, and you assume that the group is set. And can you still prove that the dimension is the fake dimension is added, or can you prove that the semigroup is Z plus? Okay, but that's how you pick out. That's how you get going on an exercise, I would say. Now, it's not maybe not quite fair because I've been thinking about these things for a long time, right? But sometimes I think of other things too. You don't believe it. Okay. No, but like but dimension is very important for K-theory and for classification. Well, for instance, it classifies vector spaces. Okay. Anyway, if someone wants to talk afterwards, that's fine.